In this video we're going to look at some properties of cubic functions. So those would be functions, polynomials of degree 3. So the general equation would look like this: ax cubed plus bx squared plus cx plus d. So a general cubic polynomial with a positive a value. So if the leading coefficient is positive, so we know what the sort of base one, x cubed, looked like this kind of. That would be if there was no x squared, x, or d terms, so these ones were all 0 and you just had your x cubed. If you had a negative a value, it would just reflect it in the x-axis, so it looks something like that. You can get sort of more variety with cubic functions though. If you have this x squared and x term, or at least one of them, you're going to get a function that looks more like this. So it doesn't just keep going up in the way this one did. It went up, came down a bit, and then went back up. Or you could get sort of a flip. You could do something like that. So that would just again be a negative a value. It's just a sort of reflection of this one in the x-axis. So let's look at some properties. Let's start with the end behavior of these functions. And again, it's going to depend on whether or not a is positive or negative. These two were had a values positive. So the end behavior as x got very large, the function keeps going up and up and up, meaning f at x also got very large, and that would be indicated by saying it goes to infinity. As x gets very negative, so in this direction here, the function, the arrow keeps going down, both of these down. So down, 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 meaning it's getting more and more negative, it's going to negative infinity. Now for the ones where a was less than 0, as x got large as you went along this direction, or this direction on this one, the function is going down. So we're going to negative infinity. Then the opposite, as x gets very negative, the function is now going up. So you're going to infinity. So notice for both cases, a positive, the end behavior is different on both sides of the function, and then the same over here, and it's sort of the reverse for a positive and a negative. But notice this end behavior is the exact same as another polynomial we looked at, the one with degree 1, the linear. So it had similar end behavior to the linear function. Different than the quadratic, but similar to the linear. Zeros, the number of zeros. Well, I've done a few examples. This one had 1, 0 across the x-axis once. 1, 0. This one had 3 zeros. And this one just had 2 zeros. So those would be our possibilities. 1, 2, or 3. You can't have more because a cubic function is only at most going to do this. Go up and then down and then up again. So, I mean, you could try to draw this any way you like along the x-axis. You're never going to be able to cross the x-axis more than 3 times with one that looks like that. But notice you will always have 1. You can never have fewer than 1 because the end behavior is different on each side, because on one side it's going up and the other side it's going down. It's always eventually going to have to cross that x-axis. So one key we're going to want to pay attention to with zeros is that the maximum of 3 zeros. And again, that's not a coincidence that the degree 3 polynomial has a maximum of 3 zeros. That followed the pattern from linear and quadratic. If you remember, a linear had 1 0 and a quadratic had a maximum of 2. So seems to be a pattern there. And then the next thing we're going to look at is turning points. So a turning point is when does it change from increasing to decreasing. Notice this one doesn't actually have a turning point. In this one you're always increasing, this one you're always decreasing, so there is no turning point. But here you're increasing, 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 and at this point you start decreasing, at this point you start increasing. So there was 2 turning points. Same with this one. Right here we change from decreasing to increasing, and then start decreasing again. So again, we're going to pay attention to the maximum. So there's a maximum of 2 turning points. So again, this number here is 1 less than the degree, right? Our degree was 3. Degree 3 polynomial, maximum of 2 turning points. So again, that followed the pattern from linear, which had no turning points. Quadratic had 1 turning point, and now we have 2 turning points. So it seems again like we have a pattern. Okay, now we're going to look at Kortek functions. So it would be a polynomial of degree 4. General equation looks like this. So highest power x to the 4, leading coefficient a. General quartics. Sort of the simplest quartic you could have would be if you just had the x to the 4 term and then the rest of these were 0. That would look very similar to a quadratic, but it ends up being a little flatter near the sort of vertex, if you will, and it goes up a little steeper than a parabola would. But again, that's for positive leading coefficients, and then you would just flip it around for negative leading coefficients. The way is negative. But with a quartic, you're going to find you can get more variety. And again, the higher we go with powers, so it's sort of more variety you get in these functions. So a quartic could end up looking like this. So it starts off kind of like a parabola, but then it sort of changes directions. It starts going down again, and then it'll go up again. And that's sort of the most volatile this one could be. And again, you could have, a negative value would flip this. So it could look something like this. And then depending on these x squared and x terms, that would determine kind of how much the one side goes up, or like how many zeros are, and things like that. But these are just a few examples of quartics. You could have sort of a wide variety, but they're all going to look kind of similar to this. Okay, end behavior. Notice the end behavior is very similar to a quadratic, to a degree 2. So notice the even. This is an even number. Quadratic was even. They seem to have similar end behaviors. As x approaches infinity, as you get bigger x values, function's going up, so it's going to infinity. As x goes to negative infinity, the function's going up, so we're going to infinity. So that was the same as quadratic. They have the same end behavior on both sides. And then for negative a values, here in both sides are going to negative infinity, you're going down in both directions. So again, that's the same as quadratics, same in both directions, and negative infinity for negative a values, positive infinity for positive a values. So that, it might appear that we have a pattern which could be generalized for even degree polynomials. That this end behavior pattern might be something we could sort of generalize. Number of zeros. Well, here we have 1 0. This one had 2 zeros. This one had 1, 2, 3, 4. 1, 2, 3. I could also have done one with none. If you had your quartic all the way above the x-axis, or also it could be below. So for a quartic, you could have 0, 1, 2, 3, or 4. Again, the maximum of 4 zeros will be important. So notice, again, that maximum number, 4, matches our degree, which was the same for linear, had 1, quadratic had 2, cubic had 3, so that looks like a rule we could generalize. The number of zeros will match, or the maximum number of zeros will match the degree. Remember, quadratics also had this case where you could have 0, but linear and cubic did not. You always had to have at least 1. So again, that looks like a pattern maybe we could generalize. Even ones appear to have the possibility of no zeros, but odd ones always had a 0. And finally, we look at end behavior. Oh, sorry, this shouldn't say end behavior. This should say turning points. So we want to look at the number of turning points. So notice there's different number of turning points on the different ones I've drawn. This one only had the one turning point right here, decreasing to increasing, and this one also had one turning point, I guess right there, increasing to decreasing. But here we have more. Decreasing, 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 turning point, increasing, increasing, turning point, back to decreasing, turning point, back to increasing. So there was 1, 2, 3. This one also had 1, 2, 3. Same with this one. That's the maximum number you could have. So max of 3 turning points. And again, this follows a pattern we'd seen in the previous, I guess, 3 examples. The maximum number of turning points is, the degree was 4, right? So 1 fewer than the degree. That was the same for cubic, which only had a maximum number of 2. Quadratic would had a maximum number of 1, and linear which had none. So that seems to be a pattern that we could again likely generalize to higher degrees.